So hi, we're back, and we will resume our discussion of the Reynolds number, which is one of the most important dimensionless numbers in fluid dynamics, especially for us in the context of astrophysics. And if just by way of a recap, you remember that the Reynolds number is defined by is essentially the dimensionless ratio of inertial forces to viscous forces. So physically, if the Reynolds number is large, inertial forces are more important, right? More important in relation to viscous forces, and therefore the flow is relatively less. The flow is effectively inviscid, right? Viscous effects are not important, and vice versa. If the Reynolds number is small, then viscous forces are more important, and so the problem can be simplified accordingly, right? So this is one way of looking at the Reynolds number. When we met last, we also talked a little bit about dynamic similarity, and at the heart of it, so dynamic. And this is one very useful way in which Reynolds numbers, that the concept of the Reynolds number is applied. And we essentially wrote down the Navier-Stokes equation in the absence of Navier-Stokes, right, which is just the momentum equation. We specialize to steady state, which is to say any partial derivatives, in other words time derivatives as discerned by the observer in the lab frame, goes to 0, and we also neglected body forces such as gravity, right. If we do that, the Navier-Stokes equation is simply rho times. So this is MA, so to speak, and the MA can be due to pressure gradients, and there's also, so that's the viscous term, and this is the pressure gradient term, and this is the inertial term, right? Maybe it's useful to write this down. Inertial term, pressure gradient term, and the viscous term, right? There's this, and then what we did something very important. We said, let's introduce the non-dimensionalized, non-dimensionalized variables. X prime is x divided by L. So you notice x prime as such is dimensionless because L has the dimensions of length, as does x. I messed it up, so let me write it again. It's just x, right? Similarly, the velocity is like that, and the pressure is minus some. And what's the logic here? The quantity L is some representative macroscopic length. Yeah. The quantity U is some representative, well, technically is an undisturbed velocity. Okay. The idea being that, viscous effects can typically be considered as a perturbation. And so U would be, say, if you're talking about, for instance, flow around a sphere, U would be the undisturbed velocity, say, far away from the sphere, where the sphere has little influence on the flow. Yeah. So you non-dimensionalize the velocity everywhere close to the sphere as well as far away with this quantity capital U, where capital U is the undisturbed velocity, right? The velocity of the fluid far away from the sphere. And you non-dimensionalize the pressure in units of rho u squared. This is the units of pressure, except you do a small tweak here. You don't quite say P over rho u squared for reasons that technically, for some technical reasons which we won't go into, we say P minus P infinity, where P infinity, we account for the fact that even at large distances from the object there can be a finite pressure. Okay, there can be such situations. If this is the case, then the steady state equation of motion, which as we wrote down in the previous thing, right? This can now be written as in terms of these non-dimensional variables. This can now be written as U like that, where notice, so I really should be having vector signs over all of this. Yeah, same for this. Yeah, notice even the gradient has a prime. Okay, we talked about this when we met last, and we will emphasize this once again in a minute. This is the all important term. Like that. Now, how does this differ from this? Look at this and look at this. Yeah? If you wish, I can write down the other dimensional version of the equation right here, so it'll be a little more obvious. Gradient of P plus mu, like that. So compare this and this. It looks very, very similar, except for the fact that you've got primes here. Yeah, no primes here. This is a completely dimensionless equation. Yeah, and in place of the viscosity coefficient, you have this 1 over Re. Yeah, appearing here, where Re is defined as U L over nu, or U L rho over mu, same thing. Okay, so excuse me for the mess, but this is what it is. So we mentioned this fact, and we also mentioned that equivalently many times we work in terms of the Navier-Stokes equation. We can also work in terms of the vorticity equation, which is often more convenient for certain circumstances. For sake of completeness, I'll simply write this down. This is the vorticity equation for viscous fluids, not for inviscid fluids where the vorticity is conserved, circulation is conserved more properly. It's exactly, and so the vorticity equation, when written in a non-dimensionalized form, can be written as like that, and this also is a prime. Even the time variable is primed. Plus the familiar 1 over Re appearing again like that. Yeah, so compare this with this, and this is nothing but, that's what the nu is, right? So compare this with this, and so you've got the primes appearing everywhere, including the time, and you've got the coefficient of viscosity being replaced by 1 over Re. Right? So you've got dimension. So look at this, and also look at this. Look at this. Very, very similar, right? So here you see it's dimensionless, right? So you can apply it to an object that's this small or this big. That's the whole point. And herein is the principal assumption, is the principal idea of this thing called dynamic similarity, right? Because this equation or this equation is written in dimensionless numbers. It does not, all you need to do is change the macroscopic length, macroscopic velocity. That's all you have to change, and the rest adjust themselves, the vorticity and other things. So if your macroscopic length scale was 5 centimeter, for instance, or in one situation, in that case you non-dimensionalize the variables accordingly. Or in another situation, if you're talking about a geometrically similar object, okay, with much larger dimensions though. In other words, the object is exactly similar to your miniature model, but the dimensions are much larger. The dimensions are 10 meters, for instance. All you got to do is plug in capital L equals 10 meters. But this equation, this dimensionless equation here, this one and this one remains the same. Okay, and therefore the dynamics of the flow around the miniature body will be exactly the same as the dynamics of the flow around the larger body, provided of course the Reynolds number remains the same. And let's go back and look at the definition of the Reynolds number. It's worth writing this down yet again. Some macroscopic velocity times some macroscopic length divided by the coefficient of viscosity, right? So now we're talking about the situation where we insist that the dynamics of the flow will be the same in the two situations, i.e. one situation where you've got a miniature model of a ship, for instance, a miniature model like this, and the other situation where you've got a full scale model of the ship, right? And you want to see, for instance, this would be water. In this case it might, well, in the larger model the actual ship is going to be sailing in water, sea water, for instance. The question is, what should be the medium in which this miniature ship is sailing, and we'll come to that, right? So here the L is much larger, whereas L is much smaller here. And u, the typical velocity here, will be something, but here it will typically be much smaller. But nonetheless, we want to ensure that the Reynolds numbers is the same in this situation as well as in this situation. Only then the dynamics can be considered to be the same as is evident from this non-dimensionalized equation or this non-dimensionalized equation, which in many situations carry the same information. Okay, and so this is the principle of dynamic similarity, and this is often used. I mean, instead of figuring out, you design a ship on the computer, for instance, but then you want to perform an experiment on it. And so how do you do this? You don't take the full scale ship and put it in water, and that would be too expensive to perform experiments on, because you've not completely figured everything out. Instead, you build a miniature model of the ship and test it out in the lab. But in order to do that, you need to ensure that the Reynolds numbers in the two situations are the same, and u and L are very different in the two circumstances. Therefore, nu has to be different in the two circumstances in order to ensure that the Reynolds number remains the same. So this is something to be kept in mind if you want to use this clever thing about dynamic similarity. It's a very useful concept. It's used to figure out things like the drag on a ship, the drag on an airplane wing, the drag on a car, all kinds of things. Okay, so having re-emphasized this concept of dynamic similarity, let's now go back. We've already discussed this, but just to reinforce, let's now go back to what we were talking about about to re-emphasize the fact that the Reynolds number is really the ratio of the inertial term to the viscous term. So we go back to Navier-Stokes, and so Navier-Stokes here, again, so I do this sometimes, I've again reintroduced the body force term. It's really not necessary, one might as well drop it, and without the body force term you see that it looks exactly the same as what we were talking about earlier, except for the fact that I'm using the Lagrangian derivative, the d over dt, which is really the Eulerian derivative plus, right, we're familiar with this. So it's a little simpler if we write it. I often switch between these two ways of doing things. Hope you can keep up with me. Right. So the very first term, this one, this guy is the first term. This is simply, if I multiply this row here, it's rho A, right? So ma, so to speak. So that's the inertia. And what is the order of magnitude of the du dt? It's roughly some kind of macroscopic velocity divided by some kind of macroscopic time. And the macroscopic time I write as what would time be? Something like L over U, right? Centimeter over centimeter per second, right? So if I substitute for this here, I get order of U squared over L. So that's the rough order of the inertial term. And the third term, this guy, okay, this gives the viscous force, and I in order to so here again, just to re-emphasize here, the nu is simply, okay, so this thing is nu. Okay, so that's how I've written things down here. And in order to get the order of magnitude of this term, this is a second derivative of u. So it would be something like u over L squared, because the first derivative, if you remember, this would be something like 1 over L. So d square over dx square would give me an L squared in the denominator, and so that's how I get a capital U, because so the order of magnitude, I replace the velocity by the undisturbed velocity, and I replace, and in order to account for the second derivative here, I have a capital L squared here. So U over L squared, essentially U over L squared, this is the order of magnitude of this quantity, right? So that accounts for the u over L squared, and the nu I simply keep it as it is, right? So this is the order of magnitude of the third term, and you got that, you already guessed it. The ratio of the first term to the third term is by definition the Reynolds number, and if you divide u squared over L divided by this, you get the Reynolds number as UL over nu, as we've been writing all along. So this is simply to re-emphasize the fact that the Reynolds number is a ratio of the inertial term to the viscous term, broadly speaking. That's one way of, that's probably one of the most basic ways of understanding the Reynolds number. Okay, now let's now go on to discuss, so having said this over and over again, let's now go, what's the use, right? I mean, one of the uses of the Reynolds number is, of course, this principle of dynamic similarity, where we can investigate flows around a small object as long as it's geometrically similar to the larger object, and as long as the Reynolds number in the two situations are the same. So that is one use. The other thing is, well, if, for instance, the Reynolds number is very low, yeah, in which case the viscous forces predominate over the inertial forces, right? So I should derive some advantage from this, from the fact that I recognize this, and so I should be able to throw some terms away and simplify the equation, right? So that's exactly what we are going to do here, and instead of considering the Navier-Stokes equation, I equivalently consider the vorticity equation, which we've seen, and this is the non-dimensionalized version of the vorticity equation, also something that we've seen just a few minutes ago. And for a very low Reynolds number, this is much less than 1, right? RE is much less than 1, and this would generally describe a situation with high viscosity. Why is that? Because the Reynolds number is UL over nu. So if the Reynolds number is very low, that means nu is high in comparison to what? In comparison to the product of U and L, right? And so this would describe a relatively viscous flow, say the flow of honey, for instance. And we know from everyday experience that honey, the flow of honey is typically laminar, right? You let honey flow, and it's a little difficult to envisage a situation where the flow becomes turbulent, whereas it's a little easier to envisage a situation where a relatively less viscous fluid like water turns turbulent, right? So hence these two adjectives, laminar, viscous flows. Viscous is obvious from here, but this adjective needs a little bit of explanation. That's what we did. So this particular equation, in the situation where the Reynolds number is much less than 1, only this term is important, right? And we consider only steady state situations where a d over dt prime goes to 0, and this becomes, so this is no longer important, and so this becomes 1 over RE nabla prime square to be precise, omega prime equals 0, and because it's 0, one might as well multiply out the RE, and you get this very familiar looking equation, right? So this is essentially the Laplacian equation in which admits an analytical solution. So this is one of the advantages of writing it this way. Importantly, I would ask you to think about what the boundary conditions would be, right? So this has two spatial derivatives, so you need two boundary conditions. So what would the boundary conditions be for a highly viscous flow? I'll give you the answer. You can think, I'll give you the answer in terms of the velocity. Both components of the velocity need to vanish on, if you're considering a flow around a solid surface, both components of the velocity need to vanish on the solid surface. This is typically the boundary condition for viscous flow. Okay, so in terms of omega prime, or omega for that matter, I'll let you figure that out. Yeah, so I'll let you think about this question. What would the boundary conditions be? Very important. Solving the Laplacian is one thing. There are general solutions, right? But in order to pin down the constants in the general solution, you do need to apply the boundary conditions. So boundary conditions are all important. One of the important consequences of this solution is that, and we will not go into this, I'll simply state this fact, is that the drag on a sphere is given by this. Okay, now let's pause for a moment and talk about what this means. If you recall, now even if you don't recall, that's all right. Imagine a situation where you've got a sphere embedded in a flow. So the flow would look like slightly disturbed around the sphere, very far away from the sphere. The flow is undisturbed with many other, relatively less disturbed streamlines like this, and so on and so forth. And this is the sphere. Not a very good drawing, but this is a solid sphere. Now, what's your expectation of the drag on a sphere, right? Everyday experience, if you're trying to, either the fluid is flowing past it, or equivalently, you are trying to move the sphere inside the fluid, right? And your everyday experience tells you that there will be some drag. It's not completely frictionless. It's not a completely frictionless situation, right? Now, if you recall, for a perfectly inviscid case, in other words, when a situation where the entire flow can be described exclusively in terms of the velocity potential, which is given by, this is just convention, the negative, and the velocity potential is given by this phi, and this is the right? And if you recall, the solution to a perfectly inviscid situation would be one where would be actually the solution of the Laplacian, like this, looking very much like this, except it's not omega there, it's actually that would be the solution in a perfectly inviscid situation, right? Inviscid flows. And the thing of it is, for an inviscid flow, you allow for infinite slip at the boundary. The flow does not stick at all. The tangential velocity is allowed to slip as much as it wants to. Okay? That's the boundary condition at the surface of the sphere. You insist that the normal component of the velocity is 0 and the normal derivative is 0. You do need two boundary conditions because you've got, but the tangential velocity as such is allowed to be just, it can slip infinitely, right? And in this situation, we will see this when we a little later during this current discussion, when we talk about lift on a ball, on a spinning ball to be precise, how exactly one comes about to the conclusion that I'm going to state. But to recapitulate, one can show that in a completely inviscid situation where infinite slip is allowed between the sphere and the flow, the solution to this equation with the appropriate boundary conditions suggests that there is no drag on the ball. This is called the Delumbers Paradox. There is no drag on the ball whatsoever. Okay, in other words, you can, the ball can slide through the fluid, or the fluid can slide past the ball in a frictionless manner, no drag at all. Now we know that this is unphysical, but this is what the solution predicts. What can you do about it, right? However, in the presence of a finite viscosity, in particular, in our case, we are talking about low Reynolds number flows, and so viscous forces are important. And when we solve this equation with the appropriate boundary conditions, it can be shown that there is a finite drag, as would be expected, and the drag force, this is the drag force, the drag force is proportional to the radius of the sphere and the first power of the velocity, and also to the viscosity coefficient. Okay, this is called Stokes Law. Very important law. This holds only for the case of a perfectly smooth sphere. There are many specializations that go into this law. It's been experimentally verified to a great degree of success, and so, but this is a very important law. I'm not going into the details of how exactly this drag law is derived from the solution to this. Okay, you can look up Landau-Lifshitz or other similar texts, maybe Kundu, the text that we've discussed in the beginning. But suffices to say that this is what this particular solution, low Reynolds number, the solution to a low Reynolds number situation predicts. Now, when we go to the next discussion, we will also look at the other extreme, in other words, the Reynolds number much larger than 1 situation, and try to see what the equivalent law would be in that situation. And then we'll put the two together and investigate some interesting behavior, because in real life situations, you often transition from a low Reynolds number situation to a high Reynolds number situation. It's not always that you can remain just in one situation. For instance, a car or an airplane, for instance, starts out slow and then accelerates. So when it's slow, the Reynolds number is relatively slow because the u is small, right? But after it picks up speed, the u becomes large enough that the u times L becomes appreciable in comparison with the nu in the denominator, so the Reynolds number becomes high. And so you are actually transitioning from a low Reynolds number situation to a high Reynolds number situation. And as you can imagine, it's very important to figure out what the drag would be in one situation as opposed to the other. Is there a reduction in drag? Is there an increase in drag as you proceed, as the velocity increases? These are all very important engineering considerations, and so we will try to understand how this thing works. So just to summarize, the result of this particular, or the import of this particular discussion, for low Reynolds number flows, only this term is important. In a steady state situation, the rest of the term, by definition in a steady state situation, this goes away. And since this is much more important than this, the equation essentially boils down to this. And from this, okay, one can show that the drag due to a viscous fluid flowing past a sphere, a smooth solid sphere, is given by this. And the main thing to note about this is that the drag force is linearly proportional to the velocity. Okay, and the viscosity coefficient also finds a place in here. This is not the case, and when we start talking about a high Reynolds number situation, we'll find that this is not the case. So we'll stop here for the time being.